You ever feel like science has its own secret language? You know, a code that describes everything from the water you drink to the air you breathe. Well, it absolutely does. And today, we're going to crack that code. So in the secret language of chemistry, chemical formulas.
So, take a look at this. C12H22O11. I know, it might just look like a jumble of letters and numbers, but it's actually a recipe. It's a super precise description of something you almost definitely have in your kitchen right now. Just stick with me, and I promise, in a few minutes, you'll be able to read this just as easily as you're listening to me now.
Yep, that's it. It's sucrose, or as you probably call it, table sugar. See, we're going to turn this cryptic-looking code into something totally simple and understandable. By the end of this, you won't just know what it means, you'll know how it means it. You're about to become a chemistry code breaker.
Okay, so every secret code has a set of rules, right? A key that unlocks the whole thing. And the language of chemistry is no different. We're going to start with the absolute basics. Seriously, once you get these down, everything else is going to just click into place.
So, what even is a chemical formula? Well, the official definition is a symbolic representation of a compound's chemical composition. But let's be real, in plain English, it's just the fastest, most efficient way for a scientist to write down exactly what something is made of. It's an ingredient list and a recipe all rolled into one.
And honestly, there is no better place to start than with the most famous chemical formula on the entire planet, H2O. Everybody knows it means water, but do you really know what each part of that formula is telling you? Let's break it down right now.
First up, the letters. These are just the symbols for the elements, pulled straight from the periodic table. Think of them like abbreviations for our ingredients. So, H stands for hydrogen, and O stands for oxygen. Easy enough, right? So our recipe for water calls for some hydrogen and some oxygen.
Okay, now for the really cool part. See this little number here? That 2 is called a subscript, and its job is incredibly important. It tells you the quantity. More specifically, it tells you how many atoms of the element to its left are in one single molecule.
So back to H2O. That subscript 2 is attached to the H. This means every single molecule of water has exactly 2 atoms of hydrogen. Not 1, not 3, always 2. It's that kind of precision that makes this language so powerful.
All right, quick pop quiz for you. You can see the O for oxygen, but there's no little number next to it. So based on what we just learned, how many oxygen atoms do you think are in one molecule of water?
If you guessed 1, you nailed it. Absolutely right. And that's a super crucial rule of the code. If you don't see a subscript, a 1 is always just understood. You know, chemists are efficient. Why write a 1 if you don't have to? So H2O means 2 hydrogen atoms and 1 oxygen atom. And just like that, you've decoded your very first formula.
Awesome, you've got the fundamentals down. But, you know, just like in any language, sometimes you want to be super specific, and other times you just want to give a general idea. Well, chemistry has different types of formulas for these different jobs.
Let's look at how this works with another really common molecule, glucose. It's the simple sugar our bodies use for energy. Now, its molecular formula, C6H12O6, gives you the exact total count, 6 carbon, 12 hydrogen, and 6 oxygen atoms. But sometimes, scientists just need the simplest ratio. That's where the empirical formula comes in. For glucose, you can divide all those numbers by 6, which gives you CH2O. So think of it this way. The molecular formula is the detailed, exact recipe, while the empirical formula just tells you the ratio of ingredients. Both are useful, just for different things.
Okay, you've learned the symbols, you've mastered the subscripts, and you know there are different kinds of formulas. I think you're ready to level up. It's time to tackle a much more complex code. But don't worry, you already have all the tools you need.
Whoa, okay, I admit that one looks a little intimidating. This is the formula for something called hydroxyapatite, and here is why this is so cool and relevant to you. This is the main mineral that makes up the enamel on your teeth. It's what makes them hard and protects them. In fact, you might even see it as an ingredient in your toothpaste. So let's figure out what's in your smile by cracking this code.
The new trick here is the parentheses, and they work exactly like they do in math class. The one key rule to remember is that the subscript multiplies everything inside it. So as we follow these steps, you see we start with the easy stuff outside. Then we look inside each set of parentheses, multiply by its subscript, and then we just add it all up at the end.
Okay, so let's do the final tally. We've got 10 calcium, 6 phosphorus, 2 hydrogen, and
And don't forget, we have to add the oxygen from both parts, a grand total of 26 oxygen atoms. See? By just breaking it down step by step, even a formula that looks really complicated becomes pretty simple to solve. All right, Codebreaker, let's bring it all home. You've learned the rules, you decoded a pretty complex formula, and now it's time to go back to where we started and really understand why this secret language is so incredibly important.
Remember this thing? The mystery formula from the very beginning. It doesn't look so mysterious anymore, does it? Now you have all the keys you need to unlock it. Let's do it together.
C12, that's 12 carbon atoms. H22, that's 22 hydrogen atoms. And O11, 11 oxygen atoms. That's it. That is the exact, precise recipe for one single molecule of sugar. You have officially cracked the code.
So what's the big takeaway here? It's really what this quote says. Chemical formulas give us this amazing insight into what things are really made of. It's not just some boring school exercise, it's a fundamental tool for understanding the entire world.
This language matters because it's universal and it's incredibly precise. It tells us the exact ingredients and their ratios. It's the foundation for writing the chemical equations that lead to new medicines, new materials, new technologies. I mean, it really is the blueprint for the physical world.